So the first question, a shipment of 20 microwaves has 5 which are defective. If your job is to select 4 microwaves and sell them, then what would the distribution diagram look like for the number of defective microwaves in the 4 that you select? So we've got to fill out this chart here. The first thing we need to decide is this a binomial or a heterogeneous distribution? Well, because binomial depends on every event having the same probability of the event happening, true or false. We do have 2 things here. We've got a microwave that's defective and non-defective, but we go with heterogeneous for this one because we know that as soon as we take one microwave, the probability of choosing the next microwave is going to be slightly different. So therefore, for a binomial, it has to stay the same, and therefore heterogeneous is the which way we use here. So we want to look at the probability of 0 defective units. We know that 0 defective is going to be, we've got 5 defective, so it's going to be 5, choose 0. And if we're choosing 4 altogether, we know that 15 are left that are good, and it's 15, choose 4, and all divided by 20, because we've got 20 altogether in the package, and 20, choose 4. And that will be the probability of 0 defective units. And 136504845 is 0.281 or 0.282, which equals 28.2%. And then for 1 defective, we get the same 5 choose 1 times 15 choose 3 this time, all over 20 choose 4. And that equals, and work this one through, we get 469.4695, so that's 4.47 really, isn't it? 0.47, which equals 47%. And then for 2 defective, we get 5 choose 2 times 15 choose 2 over 20 choose 4 again. This one we get 0.2167, which equals 0.217, 21.7%. And for 3 defective, we get 5 choose 3 times 15 choose 1, because we're only choosing 4, 3 plus 1 is 4, and 20 choose 4, and that equals, and we get 0.0309, so 0.031, 0.0309, which equals, rounded up, 0.031, which equals 3.1%. And the last one, 4 defective, would be 5 choose 4 times 15 choose 0 over 20 choose 4, and that will equal, and we get 0.001, which equals 0.1%. So the 5 numbers there for 0 defective, 1 defective, 2 defective, 3 defective, and 4 defective. Interesting enough, we add all these up, what do we get to? We should get to 100%, so 28.2 plus 47 is 75.2, plus that one is 96.9, 99.9, yeah, it's 100%, so it adds up all the way to 100%. So that's the table done. And if you look at the top of your page, we can see all those numbers as decimals have been filled into the probability there. And now to find the expected value, which is the last part of this question, we need to multiply these. So we're going to do 0 times 0.01. Come down to the bottom, so it's 0 times 0.01, 001. And then we're going to add the next 2, which is 1 times 0.031, and then the next 2 times 0.217, and then plus 3, which is the next 2, times 0.47, and then plus 4 times the next two, 0.282. And that will give us our expected value, which is going to be that 0.031, plus 2 times that is 0.434. 3 times that is 1.41, I think it is, and then plus these two. 4 times 0.28 is, not very good at mathematics, 112, 1.128, I think it is. And then the grand total, we add all these together, we get the 5, 3, doing this all in my head, which is quite impressive. 2, 3, so 3, 4, 7, 10, add 1, carry 1, 2, 6, 10, carry 1, and we get 3.03 as our expected value. Hopefully that is correct and nobody's going to correct me. 3.03. So question 2, a basketball player shoots free throws with a 70% success rate. If you were to shoot 5 free throws and drop a distribution diagram that counts for every missed shot that he might get. So we've got 0 miss, 1, 2, 3, 4, 5. So the first thing we need to decide is this binomial or heterogeneous? So the definition of binomial is the fact that the probability of each event stays the same. And as we're shooting free throws, he's got a success rate of 70%. That doesn't change. So therefore, we will have a binomial distribution. And we know the formula for this is given by n choose r, p to the power r, 1 minus p to the n minus r. And don't forget that p is the success rate, and this is going to be the failure rate of what we're trying to assess here. So we're going to look at the different probabilities. So we're going to start off with 0 missed. And that means that he scores every bucket. And we know the probability of success equals 0.7, and the probability of failure is going to be 1 minus 0.7, which is 0.3. So therefore 0 missed is going to equal 5. And that equals 5, choose 0. In fact, it's going to be 5, choose 5, isn't it? 5, choose 5. P is the percentage of success. That's going to be to the power 5, and then the probability, of failure is going to be 0.3 to the 5. So that is for 0 missed. It's a bit confusing because the 0 there missed is the same as that 0. That's what we're going to work. So this is with 5 made buckets or 0 missed, the probability. And this equals 0.168, which equals 16.8%. Going to look at 1 miss next. So if they missed 1, that means he scored 4 of them. So it's going to be 5, choose 4, times 0.7 to the power 4, times 0.3 to the power 1. And that equals 0.360, which equals 36%. Next, we're going to look at 2 missed, therefore 3 made. So he misses 2, he scores 3, and that becomes the 3 there, times 0.7 to the power 3, because he makes 3 shots, times 0.3 to the power 2, and that equals 0.3087, which equals 30%. I think that's right, yeah. Next one's going to be 4 missed. And that means he makes, 3 missed, excuse me, get that right. So we want 3 missed. So he makes 2 of them, 5 choose 2, 0.7 to the power 2, and then 0.3 to the power 3, and that equals, we get 0.1323, which equals 13.2%. Next one is going to be 4 missed. It's going to be 1 made, so 5 choose 1 times 0.7 to the power 1 times 0.3 to the power 4, and that equals 0.0283, which is 2.83%. And the last one is if he misses all 5 shots, which would be pretty disastrous, and obviously he makes none of them, so 0.7 to the power 0 and 0.3 to the power 5, and that equals 0.0024, which is 0.24%. And again, if we add all these percentages up, should add up to 100%. That's 52.8, 82.8, 83.7, 96.9, 98.9, 99.83, and yep, 100%. Perfect. All right, so now we've got to put these percentages into the box, the diagram. As you can see, we've put them into the diagram, and now we need to work out the expected value, which means multiplying and adding all these together. So the expected value will equal multiply those two together, 0 times 0.168. We're going to add those two multiplied together, 1 times 0.36. Add to those two, 2 times 0.3087, plus 3 times 0.1323, plus 4 times 0.0283, and then the last one 5 times 0.0024. So that becomes 0.36 plus 0.6174 plus 0.3969 plus 0.1132, and then plus the last one, 0.012. And that lot added together, well, if we look at our diagram, we could probably make a good guess where the answer is going to come, because we've got, that was 0.36% and that was 30%. So I would think that the answer is going to come in between 1 and 2 here. Let's have a look. We'll add them up and find out. Indeed, the answer we get is 1.4. Different colour of green, not very good. 1.4995 as our expected value, which we said was going to be somewhere in between 1 and 2, and we got a good guesstimate there. Well done, everybody. So question 3, according to a survey, 41% of US households have a soccer ball. Suppose suppose you ask five randomly chosen US households whether they have a soccer ball or not. Draw a histogram of the binomial distribution. So it tells you right away we've got a binomial distribution. With the so we're going to go through and work out each one using the binomial. And what we're going to do here is start off with working out the first one, which is going to be for 0 soccer balls, so 0 balls. And we know that it's going to be 5 choose 0, and therefore 0.41 of the percentage, the probability of having a ball, and therefore 0.59 is the percentage of not having a ball, and that answer will equal, so 0.07 and 1, so that equals 7.1%. And then 1 ball will be 5 choose 1 times 0.41 to the power 1, and then 0.59 to the power 4, and that equals 0.248, and that will be 24.8%. 2 balls, get the idea now. It's going to be 5 choose 2 times 0.41 to the power 2 and 0.59 to the power 3, and that equals 0.345, which is going to be 34.5%. 3 balls, it's going to be 5 choose 3, which we know is 10, 0.41 to the power 3, and then 0.59 squared, and that equals 0.2399. So I'm going to round that up to 0.24, which is 24%. And then 4 balls is going to be 5 choose 4 times 0.41 to the power 4, and then 0.59 to the power 1, and that equals 16.6, so 0.167, 16.7%. In fact, this last one is wrong, isn't it? It should be divided by 2, so I think it's 8.35%. Got it wrong there, sorry about that. And then 5 balls will equal 5 choose 5 times 0.41 to the power 5, and then 0.59 to the 0. So we get 0.0115, which equals 1.2%. And if we add this lot up, we should get 100%. So 1 plus that is 9.5, 33.5, 67, 68. Add 24 is about 92.8, and then 7.1 does indeed make 100%. So with each of these numbers now needs to go onto the probability, and we'll put that in right now. So now we do the expected value. It's going to be the multiplication of all of those, which equals 0, down here, 0 times 0.071. We know that's going to be 0 plus these two multiplied together. So that's 1 times 0.248 plus these two multiplied together. So 2 times 0.345 plus these two multiplied together, so 3 times 0.24 plus these two multiplied together, So 4 times 0.0835, and the last one 5. These two multiplied together, which is going to be 5 times 0.0115. And that will equal, well, that one's 0, so we get 0.248, the first one, plus 0.69, plus 0.72, plus 0.334, and then the last one plus 0.0575. Add all of them up together and we get 2.0495. So if you round that up 2 decimal places, 2.05. Excellent. Well done, everybody. And of course, we know the formula of the binomial is as such. It is the